Hello Year 12, hope you're well. Have you had a lovely half term? I hope you have. And we're back on it, we're back on electricity. Now this is the last-ish session. It's certainly the last area of electricity you need to learn about before we start to really hammer the questions and look at some quite challenging questions where this stuff comes up. Hopefully you'll have all the knowledge you need then. Right, let's have a look at the spec to start us off. Right, so what we're doing today is about internal resistance. Here we have done a lot about resistance, you know, Ohm's law and whatnot, and it does come up all the way through electricity, but this is an internal resistance. We'll come to what that means in a minute. We need to pin down what electromotive force is. What is actually electromotive force? We need to know what this term is, EMF, electromotive force. Just said that we need to know what this thing here we call the terminal PD. And you will be expected to understand that internal resistance exists and perform calculations in which it is not negligible, and there's a required practical involved. Obviously we can't do the required practical right now, but when we reconvene, probably in the new year, school year, then we'll do that. Alright, so let's just kind of nail down the theory. Right, first up, internal resistance. What is internal resistance? But first up, what is this thing we call epsilon, Greek symbol epsilon, and we'll call that the EMF, the electromotive force. Alright, so electromotive force. Let's break that down then. Electrons or electricity, motive meaning move, force meaning something pushing it to move. Right, so we know from mechanics that for anything to move it must have something pushing it, otherwise it remains stationary. Newton's first law, it must have a resultant force, and the resultant force for electricity comes from this supply of energy. We'll call this the electromotive force. If we have the cell there, and as discussed before, the electrons come in here. Now they want to do that. Why would the electrons want to come to the cell at that end here? Well, it's because of that cheeky little positive there. So they're attracted to the positive. But then when they get inside the cell, they don't really want to go away from the positive. That's where the chemical energy is done, in pushing the electrons across, and in pushing the electrons, work is done here. Work. Right, so work being energy. Could say work or energy, can't we? Right, so work or energy is done on pushing those electrons through the cell. Now when they get out of the cell, yeah, they're quite happy to race away then, because they're negative and negative, right? So what the electromotive force is basically the work done or energy transferred on a unit of charge. Now we know the energy is the joule, and a unit charge would be the coulomb. So, you know, we're saying 1 joule per unit charge per coulomb is gained. Now this is different to where we come to a resistor or whatever, because here we lose energy as we go through the component. Alright, so we come in, and this time work is done to get through it, so we lose energy. Now that one there is the potential difference, PD, is equal to the work done per unit charge. Now those two formulas are exactly the same. The symbols are different, but the concept is exactly the same, which means that the EMF is also measured in volts. V. Yeah? PD is of course measured in volts, V, and work is measured in joules, energy, and we've got coulombs again, right? So it's the same formula. That's why electromotive force is measured in V. But it basically is the energy that's gained as it goes through the cell, because the electrons have to be pushed to get through the cell. They don't really naturally want to go through that cell towards the negative end, and that energy has to go to somewhere, and that's what we call EMF. Alright, so it's all about energy. Physics is all about energy. That's EMF then. Alright, so it's the energy transferred per unit charge, or the energy gained, produced per unit charge, right? And that's EMF, right? Okay, so that's that bit done. Let's get on to this thing we call internal resistance. Now, internal resistance is something that we tend to ignore. Alright, so here we've got a very standard circuit, and it goes round through, I don't know, some sort of fixed resistor there, right? Now, what we usually say is that the only resistance in this circuit here would be capital R there, and the voltage, the EMF would supply, I don't know, whatever, it would supply 3 volts. It would come to here, and those 3 volts would only be lost across that resistor. Right, that's what we usually say. That's if. That's only if, and it's a very big if internal resistance is negligible. Right, now negligible, for those who haven't come across the word negligible, means too small to be bothered about. Yeah, so it's basically that small we don't care about it. Alright, so, but we also know from other studies that everything that electricity travels through has some sort of resistance. And that means this wire here would have resistance, so we would actually lose energy going through here. This wire here has resistance, so I suppose the same wire. This wire here has resistance, and we would lose energy here. So although we're saying we've gained 3 volts here and lose 3 volts here, actually we'd lose energy as we got all the way around. So we'd probably lose what, like 2.9 volts across the resistance, and then the rest is across here. Okay, good. Also, the cell. Now, you might have noticed, because you've been sitting around doing nothing on lockdown, that you're on your phone a lot, and you might notice that your phone gets hot. Now, this is purely because the electrons are travelling through the battery of your phone, and as they travel through, you know, the classic diagram remains true. So you've got the positive, you know, you've got the positive, and the circuitry, of course, inside your phone. Then you've got the electrons that travel through, and the more current you ask, now when you've got your screen on and your sound on and all this business, it's going to draw more current, isn't it? And the more current that you have going through, is the more electrons are going to bang into those ions, which makes the ions vibrate more. Surely you remember this from the other week, right? So they vibrate more and the temperature goes up. And in a wire, not a thermistor, what's the relationship between temperature and resistance? We decided amongst us, I don't think that it was linear, but it was certainly as temperature went up, resistance went up, not a thermistor, I might add. Now, if your phone circuitry, and certainly within the battery, the cell, is increasing in temperature, then its resistance is going to increase. And then therefore the temperature will increase, and it starts a vicious cycle, and that's why your phone gets hot when it's on. So therefore all power supplies have this thing we call internal resistance. So it's resistance that's basically, it's inside the power supply. All the bits that are inside the power supply, that is where this resistance resides. Now, it's a theoretical concept, which is why it's not actually a resistor. It's not actually a thing. It's almost like an abstract concept, if you will. Right, and how we use it is this. Right, so we've got our cell. Now our cell gives us our pure EMF. But what we say is that we imagine a small resistor that goes with it, and we call that one little r. Oh, it's very cute, isn't it, little r? And we say that that is the internal resistance. And what we do, because we say that little r is part of the power supply, you'll often see it with a dotted line. Now, I've seen a nasty question in an A2 paper that doesn't give you that dotted line, and it expects you to know, because it doesn't say that internal resistance is negligible. You must look out for that phrase, the internal resistance is negligible. If it doesn't say that, they are trying to trick you. Right, they're trying. But in most questions that involve internal resistance, you'll see this kind of diagram, and you may have seen it already pop up. You know, you might have seen it already be crept into one of the questions that we've seen. So what does it mean, right? So we must attach it to a circuit, because with no current flowing there'll be no internal resistance, right? So we've got our very basic simple circuit here. Now, just like we had up here, this one, we're going to call this capital R. Right. Now, let's throw some hypotheticals at it. Let's say the EMF is 6 volts. Okay. This is now a series circuit that comprises of 2 resistors and a power supply. You might remember from just before half term, this is what is technically known as a potential divider. Yes, well done. Right. So you've got 2 resistors and a source of EMF. Now that 6 volts then is not going to be dropped purely across this capital R, is it? Because that 6 volts has to be shared around the series circuit. That is Kirchhoff's second law, his voltage law, PD. Right? So what we say is that, let's say, I don't know, I'm making up numbers here, but 0.4 volts are lost across the internal resistance. What do we expect to see over here? Well, of course, over here then we're going to see 5.6 volts, yeah? So about 5, right? 5.6 volts, yeah? Agreed? Now if it's 5.6 volts there, that's telling me something. That's telling me that outside of the power supply, here and here, outside of there, must also be 5.6 volts. Of course, we're making assumptions about the wires having 0 resistance, but alright, so here and here is also 5.6 volts. So if I measured, when the current is flowing, if I measured this end of the cell and this end of the actual physical cell, this terminal and this terminal, then what we get is we get the terminal PD, terminal potential difference. And this would be what we would have either side of the actual power supply, be that cell or one of these power supplies that you plug in or whatever. That is the terminal PD. We can't access this, we can't access it, but we can access the terminals, and that can tell us something. So what's the 0.4 volts called? Well, often, because this is a complete waste, isn't it? This is energy that is just going into nothing. It's just going into heating the supply. We call these lost volts. Right, those are lost, it's all, or lost PD, you know, whatever you want to go with. Right, lost volts or lost PD, because that's just purely just wasted that's inside this theoretical resistor. Okay, so that's where internal resistance comes into play. Now if you look at the work I send out tomorrow or whenever it is, there's questions that involve this, and you might see, you know, what is the terminal PD, what is the lost volts, what do we call the voltage inside there. This is the basic, this is your basic kind of crib sheet, if you will. Right, that's the EMF, That's the lost volts. That's your terminal PD. Okay, as if by magic this formula has now appeared. Where's it come from? It looks quite scary, doesn't it? You know, there's a lot of letters in there and bracketing and whatnot. It's not too scary. It's just an application of Kirchhoff's law. All right. Let's look at this circuit over here. Well, from Kirchhoff's voltage law, the second law, we know that the EMF is going to equal, let's say, the voltage across the power supply, so we'll call that V subscript P for want of a better one, plus the voltage drop across R. Yeah. So we're going to call that VR. Now, Ohm's law comes into play there, and we know that the voltage across here is going to V equals IR. Ohm's law, V equals IR. So VP will be I in P and R. But R is this one. Plus I in capital R and, well, capital R. Right? Happy so far? Now, Kirchhoff's current law tells us that it will be exactly the same. What will be exactly the same, sir? I hear you. I hear you. I will be exactly the same. Why? Because in a series circuit, I will be exactly the same, because Kirchhoff's current law says at a junction it will split off. Where are the junctions here? There are no junctions. So the I will always be the same. So this I then becomes common. IR plus IR. And because it's common, it can factorise out into the brackets. So the EMF is equal to I'll just move it around because I think it just looks better with the capital in front. IR plus R. And this is the internal resistance formula that becomes very useful. And of course you can always factorise that back out to get, well, just multiply it back out again to get IR plus IR. If you know what I is, then you can start to, you know, get some numbers and churn it around, and depending on what the question wants. But that's the internal resistance formula for the basic circuit. Epsilon equals I, brackets R plus R. It's just a derivation of using Kirchhoff's law. Right, the final part of this whole journey with internal resistance would be, how do we determine the internal resistance if we don't, well, we can't really measure it, we can't really get at it with a voltmeter, because it's this theoretical concept, it's not actually real. Well, what we do is we use practical methods. So this time I'm going to use a variable resistor, and what I want to know is what is little r here. What's little r? This is big R. Okay, and we use that circuit, and this is your required practical, so we will do this again, so don't worry about it. Okay, right, so what do? We can get at the terminal PD here and here, but we know that the terminal PD here and here will be the same as here and here if the wires have negligible resistance, which actually they do. If they don't, we've got other problems, but we know that this PD will be the same as the terminal PD. So we can assume that the PD across here, and we'll use a voltmeter to measure it, is the same as the PD up here. Okay, happy with that concept? Brilliant. Right, what we're going to do then is we're going to vary the current going through. We're going to vary the current going through, well, around the series circuit, right? So we know that I is going to be the same at all points. But whenever we change R, then I will change with it. And we also know that as I gets greater and greater, then we're going to get more of these things that we call lost volts across here, because it's going to get hotter and hotter, so we're going to lose a greater amount within the power supply. Okay, So what we do is we basically we look at this V against here, but what we're going to do is actually we're going to change the current and we'll measure the terminal PD. And what we're going to do is we're going to plot it against each other. So I'm just going to put like arbitrary values in, nothing of any value. So we'll call that I maybe milliamps or amps, it doesn't particularly matter. And we've got the terminal PD up here in volts. A bit naughty of me, sorry. Right, okay. And what we find is that as the current increases, i.e. we allow less resistance in the variable resistor, as the current increases, then the terminal PD decreases. Why would that be the case? Well, I've just said we'd get more lost volts due to heat. So as the current increases, the terminal PD decreases. And it forms a linear pattern. Should have done this in a different colour, right? Okay, so it forms a linear pattern, and obviously, you know, there might be a bit of leeway either side, but it will be linear in a kind of negative, kind of gradient kind of situation going on there, and that's what we get. Important points to note: we have a y-intercept. What's the significance of that? We have a linear gradient. What's the significance of that? And right, so to get our internal resistance, which is ultimately what we're going to try and find out from this power supply, we use our internal resistance. I'm going to change colour. Yeah. Right, epsilon equals I R plus R. That's what we just worked out in the last section, if you will. I'm going to expand it back out. Epsilon equals I R plus I little r. Okay. Now IR here is what we were measuring up here, wasn't it? The terminal PD. So I can substitute that with epsilon equals V plus I little r. Little r is what we want. I now need to turn this into a linear equation that matches what I've got up here. So you'll remember I've got to do a bit more work on this, but y equals mx plus c. Now in this case here, the y is the PD. Now I need to get that on its own. Right? At the minute, it's not on its own. So I need to rearrange. Yeah. So I'm going to chuck the IR over to the other side. And I'm going to be left with epsilon minus IR equals V. It's not very tidy. Also, the I here is on the x-axis, isn't it? Right? So I need to get I into here. So just a quick rearrange. V is now on its own. I'm going to have to put minus IR here so that the I is now in the x plus epsilon. So hopefully you can now see that the y-intercept up here is now epsilon. The y-intercept is the EMF with no current acting. Alright, so that's a useful piece of information. The y-intercept is the EMF with no current. The what is the gradient then? Well, the gradient is a negative gradient. If we took delta V over delta I, it's actually V is going down, so we're going to get a negative gradient, which means that the gradient equals minus R. But it's a negative gradient, so it will come out as R anyway. Right? So therefore, and this is the key point to it, the internal resistance is equal to the gradient. It's the negative gradient, but it's negative anyway. the gradient of, no, I don't know, it's an IV graph, isn't it, really, to be honest, but it's a bit VI graph for this circumstance, right? And what was the y-intercept? The y-intercept was the EMF of the power supply. So using this technique, this practical technique, which is a required practical, you can gain what the internal resistance of the equipment is, be it a cell, be it a power supply, be it a lemon battery or a potato battery or one of them mad things that they do. And we can work that out from there, okay? And a lot of the questions on internal resistance are basically about that, and about the concept of this lost PD. You know, what would you get? Why, if the current got higher, would you get a lower reading across the volts and stuff like that? But we'll come across these questions. Right, that's that then. You might want to go back and just make key notes as you go. Just a quick recap. Right, the EMF is the energy produced or energy gained per unit charge, per coulomb. Right, make sure you put unit charge. Don't just put charge. If you're going to put charge, don't just put charge, because it's 1 unit is 1 coulomb. Alright, and it's the energy gained as it pushes it through the cell, which is then used around the circuit. The internal resistance is what we have because of the internal conditions of the power supply, and we get this thing lost volts here with the terminal PD outside. The terminal PD is the only really physical thing that we can do, and we derive this formula, which is what we used with the graph, which is epsilon equals I R plus R. Okay. The EMF is what would sit on this cell without any current, and that we derive that from the graph. The graph from the practical thing here, we take the current, we change the current, and we measure the terminal PD. And as the terminal PD goes down, as the current goes up, because of the lost volts, and the gradient of it is negative R, and the y-intercept is epsilon. Okay? So all that's left to do now is to smash a couple of questions, make sure you've got the concept, and work it from there. Right then, that'll be it from me on that one. It looks like I'll be seeing you very soon, probably from the 15th onwards. Don't know if it'll be every day, may only be a couple of days of the week, may even be once, twice, and then I won't see you until the new year. But we'll take it as it comes out, guys. Alright. Hope you're well. Hit me up on the email if you need to chat to me or on show my homework or whatever. Speak to you soon. Bye bye.